All right, in section 1 of chapter 3, we start to get into the topic of association. Things change a little bit from chapter 2, and I want you to start thinking along these lines where, chapter 2 we were just all into distributions. Okay, that last section, especially the normal distribution. Okay? When we're getting into association, expect things to look a little bit different. Okay, the common theme is we're still looking at numerical data. The difference now is we'll take two variables, one of which we'll call our explanatory variable. The other we'll call our response. And when we're examining an association, that typically takes place on a scatter plot. It's the best graph to use if you want to look at a comparison of two variables, both of which are numerical. Okay, kind of a funny example that our book shows. I shouldn't say funny, kind of an important one too. I mean, there's these two things fit the criteria of explanatory and response, and it's been studied and analyzed, and how legal limits on alcohol consumption are set, right? We don't need to get into all that, but we do want to identify the explanatory and response. The explanatory you can always think about as your X variable. In this case, it would be the number of beers consumed. And your response variable would be your blood alcohol level. Notice both of those variables are numerical. And for each piece, like for each individual, we could gather both of those pieces of data and plot that as a coordinate point. That would set us up to look at a possible association between the two. Now this one's really interesting here because there's a couple different, I think, like the way I read it, a couple different explanatory variables. Gets into, like it mentions income and debt, right? The response is really clear, it's the amount of stress. But then this explanatory side of things is really interesting. Okay? It mentions debt, it mentions income. Both could influence students' perspectives on debt and the amount of stress that they have. So what I'm going to say here is, I think it could be either one. You could examine the amount of debt. Perhaps the higher the debt, the more the stress. But then I'm going to throw on here, I think you could also say the amount of income, because that seems like another variable that could impact stress as to how students feel about college and debt and all that kind of stuff. The higher the income, you may have student perspectives that are just not as stressed out about it because, yeah, sure, college tuition is a bunch, but you feel like you've got a really good plan to afford it and make it work. Is there a possible way that we could take those two X variables and have a income to debt ratio that kind of examines how much income a student has relative to their debt? And if they have low income and high debt, that could be really stressful. Yeah, there could be some way to do that. That would be, we'd have to find some way to measure that first. It could be really simple, it could be a little more complicated. Okay, so this one I kind of think leaves the door open to a couple different possibilities. All right, over here, sorry about that. I had to get up and the lights turned off in my room and I had to go turn them back on, which took a couple seconds. All right, so this kind of introduces a 4-step. I vaguely follow it on this one. I'm just trying to get you open to the concept. We really get serious about it, like chapter, honestly, 8. We kind of dabble in it a little bit, but it basically breaks longer problems down into simpler ones. Okay? All we're after here is to make a scatter plot of this data about some items from the McDonald's menu. So the state step basically just says what you're going to go do. Like I'm not going to fill in these parts. You certainly can, because if you didn't do this problem with a 4-step, I would be fine with that. I just want you to introduce the steps. The state, you basically just lay out what you're going to do, what you're after. In this problem, we want to look at a possible association between fat and carbs. Actually, carbs and fat. We're going to say carbs is the explanatory and fat is the response. The plan step is where you're like, this is how we're going to do it. Okay? Well, we're going to make a scatter plot. Right? It's pretty straightforward. We're going to take a look at the data through a scatter plot. And then the do step, you actually do it. Go make a scatter plot. And then in the conclusion, you kind of wrap it up by saying, hey, here's what we saw. If you wanted to pause for a minute, you certainly could. All I'm doing is plotting these points to make a scatter plot. And there you have it. Okay? Now in the conclusion, because like we see a scatter plot here, and you might be thinking like, oh, great. What do I say? What would we want to follow up with to describe that? And there's a few things, and I'll clarify them on the next page. Okay? The first thing I would say here is the association appears to be positive. Which means as x goes up, it appears to some extent there's an association that y also goes up or increases. Okay? If the opposite was true, we'd say it's negative. If we're describing an association, we always comment on that. We call that direction. 2, strength. Weak, moderate, strong. I would say it looks moderate. It doesn't look super strong. And then we like to comment, does it look linear or do the points really look to form a curve? They kind of look linear. Okay, moderate, positive, and linear. So, this is a big point that I want to get to, because I just want to distinguish between the two. Everything that I was commenting on above is what we would call an association. Okay? That's not a very bold term to use. It just basically means one variable is changing in a similar fashion as another. Are the two related? Who knows? Okay? To answer this question, okay, we'll really explore it in Chapter 4, but right now the answer is overwhelmingly no. Okay? you're pretty safe for the rest of Chapter 3 to just not jump to that conclusion. And it gets tempting. And the reason I want to talk about it is, okay, we talked about things we describe with an association. This goes back to the McDonald's problem, where I said 1 is strength, weak, moderate, strong. 2 is direction. And 3 is linear or nonlinear. What you guys have to be really careful of is on a problem that shows a really, really strong association, it has a tendency into, like if there's a follow-up question to say, hey, do you think that X is causing the change in Y, you get suckered into saying yes. You really don't want to make that jump to causation, but you only did it because the association was really, really, really strong. Okay? Really strong associations still don't imply causation. Okay? There are criteria for causation. We're just not going to explore them for a little while yet. All right, there is a measurement. In class, we might take a look at it a little bit. It's called R. We'll get it off our calculator. This lesson has a calculator tutorial to go with it. I'll do 2 things. Show you how to make a scatter plot and then calculate R as well as the line of best fit. So here is kind of generally how R works. Like the number one thing I want you to know about it is it measures how linear the association is. And that really goes back to strength. When we say that the association is strong, it probably means that we have an association that looks very much linear. That's what R measures. So if you had an association that's like really strong, but it looks to be like an exponential curve, R probably isn't going to be that strong. It gives you a bunch of examples here. R is always between -1 and 1, right? If you had an R value that is like 0.9, you're saying that those points almost perfectly form a line. In fact, if R is 1, that's what it tells you, is the scatter plot that you made, those points actually form a line, like exactly. Here's -0.99, because R will also give you direction. If you have a negative R value, oh, wait a minute, that association's negative. Okay? That association's negative. And then you can see as it gets closer to 0, like right here, there's like no association at all. It's just kind of a random scattering of points. Okay, the scatter plot can be very helpful, which is why I'm going to show you how to make it on your calculator in that tutorial as well. Now this, I will refer to some R values. Keep in mind, I will get them off the calculator. You may have come across the formula for R in the book. I might show you 2 in class. It's ugly. We might do some with it just to kind of see how it works, but not a lot. Okay. All right, I got another scatter plot to put together here. Here's our weight. We got these like a baking mixer type thing. And then over here we have price. And we're looking to see, are the heavier ones more expensive? Sometimes it feels like things are like that, where if it's bigger and heavier, maybe it's more durable, better built. I don't know. Again, we're not getting into like the whole causation thing because we're just looking for an association. All right, now on one hand, I could just describe this as we did before. I'd say it looks to be moderate, looks to be positive, looks to be linear. It's not, the scatter plot you get doesn't seem that much different from the McDonald's data. It seems pretty similar, okay? Now off our calculators, we could get our R value, which really backs that up because it's 0.74, right? It's quite a ways from 0, so yeah, there's some kind of linear association. It's not that close to 1, so it's not super strong, but it's moderate and it's positive. Okay. The point here that I want to show you is how influential this measurement is. Okay. How influential it is. This last point they keep talking about is right here. It's kind of a goofy one because it's so different. We wouldn't call it an outlier because it still fits the association. It's way lighter, but it's also way cheaper. Right? For us to have an outlier on a scatter plot, we would need a blender that's like really, really light and expensive or really heavy and cheap. Right? That it goes against the association we saw. So on our scatter plot, that point's here. And this next question says, hey, just take it off, right? Get rid of it. I could go to my calculator and see R goes down to 0.56 if I take it out. Okay. Then it says, hey, wait a minute, in number 4, what if that mixer actually stayed at $30, but it weighed 25 pounds? What if it was over here? Again, if you kind of think about drawing in a line of best fit, you're like, looks like the association is going to get weaker still, okay? And it does. Okay, we had 11 pieces of data. I'm messing around with one of them. Took it out, okay? Because it was a piece of data that fit the trend, but then I took it out, then I moved it, right? And R is quickly moving towards 0. Now, one last thing we're going to do with it is now we find out here that, wait a minute, there's some new titanium blender that's back at 8 pounds. So our point isn't here anymore. It's not here anymore. We go 8, and it's got but it seems like it's really, really good. It's light and it's amazing. It totally defies our association, right? Our positive association was if it weighs 8 pounds, it should be cost-wise pretty cheap. Nope, 8 pounds, $500. The lightest and the most expensive. I go recalculate R. Negative 0.077. Okay? The association is virtually gone from messing around with 1 point. Okay? That 8-pound blender, if it was $500 instead of 30, our moderate positive linear association is basically gone. To summarize that, and this is something that's very important to know about R, we would say that it is highly influenced by unusual points. Okay? Let's make a note there. Those are points that don't follow the associations. All right, last thing here is don't get too into R by itself. We'll see in the next section that we have to add a little bit to it because it can be a very misleading number. I'm plotting some data here. Points from a table for an association that I happen to know is very, very nonlinear. Because if I were to connect those points with a nice curve, right? Doesn't R measure how linear the association is? But these 10 points give me an R value of 0.97, because from 1 to 10 for a quadratic, you know, if I were to draw on my kind of my line of best fit, they're not that far off, right? Be aware of this, okay? If you see, I mean, the whole point of this is we'll have a way to handle it, okay? Because what's going to happen here as we go beyond 10, we're going to see that this line isn't going to fit very well anymore, right? The line is going to go one way, and the curve is going to increase faster, and all of a sudden, they're not even going to be close, okay? But point being, don't fall in love with R. You know, to just say, oh, R is 0.97. We have a super strong linear association. We might, but we should back that up with a little bit more checking on our scatter plot to see, hey, okay, R is close to 1, and yeah, we're really convinced that the data is linear too.